Hi there! Welcome to the 16th episode of the Synth project, where we are going to build a synth together. Now that the Softpot is ready to be used, we need to create a new module, a Softpot controller, which will provide us the control voltage extracted from the Softpot itself, along with a gate signal and a trigger signal. This module will be useful to control a VCO, but can be also used for other purposes, for example to control an envelope generator, or a VCA, or even a filter, a VCF. Let's explore how this module can be made. Here is the schematic of the controller. Header H2 on the upper left is connected to the red, white and black wires coming from the Softpot through the module panel. Pin 3 of the header goes to the plus 12 volts through a couple of resistors in series that add up to 3.57K. These resistors are used to limit the control voltage to the maximum value of 10 volts required for our synth. Pin 1 goes instead to ground. These two pins are basically used to power up the two ends of the Softpot so that we can take the control voltage on its center pin, which is connected directly to pin 2 of the header H2. The control voltage coming from pin 2 of this header goes directly to an impedance adapter built around the op-amp U3.2. The output of the op-amp is the actual output of the control voltage and goes directly to the header J3, which will be connected to a dedicated jack socket on the panel. The Softpot itself is not capable of generating any other signal on its own, so since I want to also have a trigger and a gate signal available on the controller, I added some circuitry to provide these two signals. Let's start looking at the generation of the gate signal. The gate signal is supposed to be a TTL level signal, which is either 5 volts or 0 volts, a 1 or a 0. This signal goes up once a note is being played and goes down once the note is released. These are equivalent on our Softpot at the moment where we start pushing on the Softpot and the moment when we stop pushing. In the first case, a positive voltage is generated. In the second case, there is not going to be any voltage at the cursor of the Softpot. In that case, resistor R5 takes care of forcing the signal at the input of the op-amp U1.1 to 0. So at the input of the op-amp, there will be either a 0 volts or any voltage between 0 and 10 volts. Note that the op-amp U1.1 has the inverting input connected to ground through the diode D2. Because of that, it operates as a comparator, which will output a 0 until a non-null voltage is applied to the non-inverting input. At that point, it will output about plus 12 volts. The diode is there just to make sure that the output will be able to go to 0, because it puts the inverting input to a voltage slightly negative in respect to the ground, thanks to the diode D2. If we connect the inverting input directly to ground, the op-amp output will always provide the plus 12 volts. So now we have a positive voltage of value plus 12 volts every time a control voltage is emitted by the Softpot. But since we need a plus 5 volts for the gate signal, we cut the plus 12 to plus 5 volts using a Zener D1, which causes a voltage drop on the resistor R4 enough to provide a 5.1 volts at the non-inverting input of U1.2, which is configured to work as a voltage follower and therefore is used to lower the impedance of the signal available at the Zener. And so, at the output of the op-amp U1.2, we have a plus 5 volts every time we generate a control voltage with a Softpot. Otherwise, we will have a 0, and that is exactly what we wanted as a gate signal, which we can extract from header J1, which will be connected on its own jack sockets on the panel. The trigger signal can now be obtained easily by differentiating the gate signal, and that is done by capacitor C4 and resistor R7. The output of this differentiator goes to op-amp U2.2, which is configured the same way as U1.1. This way, this op-amp will be able to convert the spike of the non-inverting input to a short squared pulse. resistor R6 and zener D3, make sure that this square pulse is stopped at 5 volts, and so at the output of U2.1 we have an actual TTL-like trigger signal. Note that when the gate signal goes down, there is actually another pulse that is generated by the differentiator. This pulse, however, is negative, but it will not be propagated toward the output, because the zener, since it will be directly polarized by this pulse, it will shunt it directly toward the ground, thus eliminating totally it. We can therefore retrieve at the header J2 a single positive pulse generated when the gate goes high, and that is our trigger signal. The signal can be extracted on its own jack socket on the front panel, which will be connected to J2. And now one last note about this circuit. The op-amps used in this circuit come in pairs on a single chip. U1.1 and U1.2 are both inside the same integrated circuit, and so are U2.1 and U2.2, and similarly U3.1 and U3.2. However, we do not use U3.1 because we only need in total 5 op-amps in this schematic. The extra op-amp has therefore its inputs connected together so that it is practically disabled and will not interfere in the functionality of the rest of the circuit. And as usual, to decouple all the op-amp power supplies, each integrated circuit has its own pair of 0.1 microfarad capacitors between the supply voltages and ground, and they will be mounted close to the power pins of the ICs to minimize resistances and maximizing their effect. Let's now talk for a moment about the connection between the softpot and the header H2. I could have just connected the two sides together, as described by the schematic itself, but I wanted to have a little more flexibility and be able to invert the direction of the voltage changes on the softpot. By that, I mean that I wanted to be able to connect the softpot so that when I move my finger from left to right, the control voltage increases. But I also want to be able to do the opposite. In other words, I want to have the voltage increase when the finger moves from right to left. To achieve both functionalities, alternatively, I designed this as a simple circuit. Basically, I put a DP-DT switch in between the softpot and the header H2. With the switch in one position, I have the positive voltage applied to one end of the softpot and the ground applied to the other end. With the switch in the other position, I will have the positive voltage and the ground switched around, and so the voltage of the cursor will change in the opposite direction. Nothing complicated about that, and so I will be able to make this happen by a few simple connections directly on the back of the module panel. This is the circuit mounted on a breadboard. This potentiometer is used to simulate the softpot, and this is the actual circuit. You can see the three ICs over here. Each one of them has two op-amp inside of it. Here we have the output for the CV, the control voltage. Here we have the output for the trigger, and here we have the output for the gate. So now I'm gonna power up this circuit and we are gonna see on the oscilloscope what's going on. So first of all, let's take a look at the control voltage. So I'm gonna put this on the ground, and this one here goes here. There you go. The potentiometer right now is all the way on the left, so it won't conduct anything, it won't provide any control voltage. And now let's take a look at the oscilloscope right over here. Let me zoom in so you can see better. So basically we have two traces here. The yellow one is the control voltage, and the blue one will be used to take a look at the gate and the trigger signals. First of all, I'm gonna move the potentiometer now, and you can see that I can basically make changes to the voltage, to the control voltage. You can see I can go up and down, and right now we don't see anything else on the oscilloscope. But now let me connect the other probe of the oscilloscope, and I will start with the gate for now. So this goes to ground again. and the gate output is right here. So let's take a look again at the oscilloscope now. So right now we don't have anything, either on the bottom or on the top, so no control voltage, and of course there is no gate signal. Now I'm going to increase the control voltage from 0 to something above 0. And look, here is the gate that is now active, so now it's all the way up to 5 volts, and while the signal is right now 1.2 volts. If I change the control voltage, you can see the gate doesn't change, but as soon as I put the control voltage to 0, there, the gate signal ends. And now we don't have anything else. Let's do it again. Signal and 0. Let me do that so you can see it for its entirety. So here goes up and here goes down. So this was the gate signal and the other one was the control voltage. Now let's move the oscilloscope probe to the trigger so we can see what happened for the trigger itself. So I'm gonna move the probe from here to here, which is the trigger output, and let's give it a try again on the oscilloscope. So look at what happened as soon as I increase the control voltage. You see there is a pulse here, a square pulse, and that's it. Now whatever I do, there is nothing else over there. That's the trigger signal. I go to 0. Now that I am on 0, if I do that again, here you go. And I can do it several times, see? And basically there is a pulse, which is a trigger, every time a signal is outputted on the control voltage output. See? There you go. And this is it for our test. Well, we can do one more thing actually. Let me move a probe from the control voltage to the gate now. So now we will see on the yellow trace the gate, and on the blue trace the trigger. Look when each one of them goes out. See? The trigger happens at the beginning of the gate, and then nothing more. See? So and this is exactly what we wanted, and we will use in the future these new two signals, the gate and the trigger, for starting and producing even more interesting things on the synthesizer. But this will be a subject for another video. Now that we have designed and tested the Softpot controller, we will have to create a PCB and a module case for it. We will have to put everything together and finally install the new module in the Synth rack. At that point we will have the first of our viable interfaces to make some interesting sounds with the VCO we already have. But that will be the subject of our next video on the series, so make sure you have subscribed to the channel and that you have activated and enabled the notifications for it, so you won't miss any further episode. In the meantime, I'll see you in the next video, and as usual, happy experiments!